Hello everyone, this is Mona, Sama, and Farida. Today we're going to present our milestone regarding our project. So this is the table of contents, and we'll start with the problem summary. So our problem is to do brain tumor segmentation using MRI scans to detect whether or not there's a tumor.
Moving on to our chosen dataset, it contains 369 brain MRI images for patients, where each contains 155 image slices, summing up to around 57,000 images contained in four primary files: the training metadata, survival info, name mapping, and metadata. Uh, and here is a sample of one of the patient MRIs with the 155 slices, and each of which contains four channels, along with the ground truth. And here's the related work.
So from this related work, we chose the two-path CNN as our model, which basically takes two inputs from the image and then assembles them together after several activation functions. And then the output is the labeling to the image, whether this image has a brain tumor or not. For this project, we proposed 5 updates exactly. The first one is the attention gates, which focuses on the most relevant region in the MRI image to predict whether it has a tumor or not. Second is using mini-batch gradient descent instead of stochastic gradient descent due to its limitations and poor performance in case of class imbalance. Third, we wanted to use skull stripping as a pre-processing technique in order to enhance our image's quality and our model's performance and with it. Then we wanted to use CAM to visualize and understand how our model makes its decisions regarding labeling the images, whether they have a tumor or not. And lastly, we wanted to use UNet in an ensemble with the two-path CNN in order to enhance our model's performance and extract features from the two-path CNN as well. And how we're going to measure our performance, which is through these 4 performance metrics. First one is the dye score, which is the dye similarity coefficient, which measures the degree of overlap between the model's predictions and the ground truth. This value ranges from 0 to 1, 0 meaning no overlap, and 1 is a perfect overlap. Second, we wanted to use sensitivity, which is the true positive rate. Third, we wanted to use the true negative rate. And lastly, we wanted to use the F1 score, which is calculated using precision and recall. Next, we wanted to talk about our implementation, the things we did and the issues that we faced. We implemented the skull stripping, two-path CNN, and CAM, and this is what skull stripping is.
Moving on to our first step, which is skull stripping. So basically, it's also known as the brain extraction, where it removes non-brain areas before normalizing the brain. It's also useful for anonymizing the brain scans, and it's a pre-processing step, of course, and it improves the model's robustness. And as you can see, here's an example where the original image was applied to a color mask and was also blended, and it's either a color mask or a white brain mask, and the final output, which is the same as the input basically. Moving on to the Kami and contour edge detection. This one detects the abrupt local changes in the intensity of the image, and it smooths the brain to eliminate noise, and then it finds the image gradient. So basically, it works by stripping the MRI image to then blur it and apply the Kami edge detection. And finally, it identifies the contours and extreme points. It crops the image and it resizes it if it's necessary.
So for our model, we started by training and testing using the traditional 80 to 20 split. However, we had limitations during the testing period due to the size of the data. During the architecture of our model, we used ReLU and sigmoid as activation functions in our dense layers. We also used same padding and batch normalization for more effective analysis. And lastly, we optimized using stochastic gradient descent as a default in order to see how the model performs without any modifications. And this is basically the summary for our model, where you can see each layer and the output shape for each layer, which is the same due to using the same padding, and the parameters per each layer. And you can see here that the total parameters are around 400,000, with the trainable parameters being the majority of them, which is good because it helps our model being more customized, which improves our performance even further.
Afterwards, we started implementing the class activation mapping, also known as CAM, This is used to interpret the predictions. So basically, it explains which regions of the image contribute the most to the network's prediction of tumor presence, and requires an average pooling layer, and it does feed forward. It also reduces the dimensions while increasing the features, and it gives weights to the features depending on their effect on the likelihood of that input image belonging to a particular class. And so this is the expected outcome of the CAM. So what we did is that we added a global average pooling layer to our two-path CNN, and this reduced the feature maps to a vector of size of equal size to the number of output classes. And afterwards, we expect the results to be overlaid and to highlight the regions that the model considers the most relevant for the classification. And so to why we are saying this is the results we're expecting, it's because we already started implementing the CAM and we already were able to run the model. However, we weren't able to fit the model to our data set. And that's because due to full memory, the data set used our RAM to full capacity and it produced these errors. So even though we were able to implement the model, we weren't able to fit it to our data set. And we're currently working on this issue by trying to work in the lab. And then for the conclusion, to conclude our project so far, we already did the skull stripping, which basically did effective pre-processing to identify the local changes in the intensity of the image. We did the two-path CNN model, and we optimized it when needed. And as we said, we need access to stronger GPUs and bigger RAM to be able to do the testing. And we already started implementing the CAM as well to focus on the places in the image or the features that affect the model the most. So this is our progress so far in a checklist. As I said, we did the model implementation, we did the skull stripping, we started with the CAM. Now we need to optimize the model further. We need to add the attention gates, and lastly, we want to implement a UNet model and ensemble it with the two-path CNN. And this is our team contribution, and that's it. Thank you so much.
والله